You have probably looked at a picture of the solar system and believed you understood it. The planets neatly arranged around the sun, the distances small enough to fit on a single page. Everything feels familiar, safe, easy to trust. But right now, you are misunderstanding something very large. Try to imagine this instead. You shrink the sun down to the size of a basketball. At that scale, Earth becomes a tiny black peppercorn, less than 2 millimeters across. And that tiny peppercorn is not sitting nearby. Hello, and welcome. This is Bedtime Science Stories. A quiet space for slow scientific journeys where you can listen, reflect, and let your mind gently settle before sleep. If stories like this bring you a sense of calm, you are welcome to stay a little longer by subscribing to the channel. Now, let's imagine together. Right now, you are standing on that tiny peppercorn, drifting silently through a cosmic ocean so vast that the human mind has only just begun to touch its edges. And from that small place, we begin to look again at the entire solar system as it truly is. That peppercorn is more than 26 meters away from the basketball-sized sun, separated by a space that is almost completely empty. Between those 2 points, there is nothing. Not planets packed tightly together, not a crowded system in constant motion, but silence and distance. Most of the solar system is not made of objects. It is made of space that light itself takes minutes to cross. When we talk about distance in space, we usually reach for numbers, kilometers, millions, billions. But the human mind was never built to feel numbers that large. So instead of measuring space by distance, it helps to measure it by time. Light is the fastest thing in the universe. Nothing moves quicker. Nothing shortcuts its way ahead. And even light takes time. Right now, sunlight leaves the surface of the sun and travels through empty space for 8 minutes and 20 seconds before it reaches your eyes. During those 8 minutes, Earth is already moving. Clouds shift. People take their last sip of coffee. Someone somewhere closes their eyes to fall asleep. If the sun were to vanish in this exact moment, you would not know right away. For 8 full minutes, the sky would still look the same. Gravity would still feel normal. Daylight would continue as if nothing had changed. Space rarely gives us simple answers. When sunlight continues past Earth, it does not slow down, it just keeps going. To reach Jupiter, light needs about 43 minutes. Almost an hour of uninterrupted travel through emptiness. No sound, no resistance, just motion. By the time that same light reaches Neptune, it has been traveling for nearly 4 hours. 4 hours of straight-line motion across a system that, on diagrams, looks compact and manageable. But in reality, it is anything but. Numbers whisper more than they speak. This way of measuring distance through time quietly changes how you feel the solar system. It stops being a collection of objects and becomes a sequence of waiting. Waiting for light, waiting for signals, waiting for information to arrive. And this waiting is not abstract, it shapes how humans explore space. When scientists send commands to a spacecraft near Jupiter, they do not watch the result in real time. They wait. When something goes wrong, there is no instant correction, only patience. Silence is also a kind of data. This becomes even clearer when you think about Voyager. Voyager 1 was launched in 1977, long before smartphones, long before the internet became part of daily life. It has been traveling for nearly half a century. For about 40 years, Voyager moved outward through the solar system, slowly crossing the region dominated by the sun's influence, not racing, not escaping dramatically, just drifting forward, year after year. Even now, Voyager is not truly outside the sun's reach. It is only beginning to touch the boundary where the solar wind fades and interstellar space becomes dominant. From a human perspective, 40 years feels like a lifetime. From the perspective of the solar system, it is barely a step. This difference in perspective is important. When you imagine the solar system as a place defined by time rather than distance, it begins to feel slower, deeper, less like a machine and more like an environment. You start to realize that space is not empty in the way we usually mean. It is empty of matter, but full of duration, full of waiting, full of long pauses between cause and effect. Light carries information, but it never arrives instantly. Every image you see of the sun is already 8 minutes old. Every photograph of Jupiter is almost an hour behind reality. Every view of Neptune is history by the time it reaches you. We live slightly in the past all the time, and yet this delay does not disconnect us from the universe. It connects us more deeply. It reminds us that understanding requires patience. As you listen and as your thoughts slow, you may begin to feel it too. The solar system is not rushing anywhere. It unfolds on timescales that encourage stillness. In space, distance is measured not by how far something is, but by how long you are willing to wait. When you look at Earth from space, it does not announce its importance. It does not glow brighter than the others. It does not appear larger, faster, or more dramatic. It simply exists quietly in a narrow region around the sun where temperatures allow water to remain liquid. This region is often called the habitable zone, but the phrase can be misleading. Being in the right place is only the beginning. Space rarely gives us simple answers. Earth is not special because it orbits at the correct distance alone. It is special because many conditions align at the same time in the same place for an extended period. And those conditions are fragile. One of the most overlooked factors is the moon. The moon is unusually large compared to Earth. Its presence stabilizes Earth's axial tilt, the angle at which the planet rotates. Without this stability, Earth's climate would swing wildly over geological time. Seasons would become extreme. Ice would advance and retreat unpredictably. Life would struggle to maintain continuity. Instead, the moon acts as a quiet anchor, keeping Earth's orientation steady as it moves through space. A small adjustment with enormous consequences. Numbers whisper more than they speak. Another invisible protector surrounds Earth at all times, the magnetic field. Generated by the movement of molten iron deep within Earth's core, this field deflects charged particles streaming from the sun. Without it, solar wind would gradually strip away the atmosphere, as it did on Mars. Air would thin. Water would vanish into space. The surface would become exposed and barren. You cannot see Earth's magnetic field, but every breath you take depends on it. Silence is also a kind of data. Beneath your feet, another slow process is constantly at work. Tectonic plates move, collide, separate, and recycle Earth's crust. This motion regulates carbon dioxide over long timescales, acting as a planetary thermostat. Volcanoes release gases, rocks absorb them. Weathering locks them away again. This cycle prevents Earth from becoming either a frozen world or a runaway greenhouse. It is not fast, it is not precise, but it is effective. Water plays a similarly balanced role. Earth did not receive too little water, like Mars, where rivers once flowed and then disappeared. It did not receive too much, like ocean worlds where land never breaks the surface. Earth received enough to shape continents, moderate temperature, and support complex chemistry. Liquid water moves heat around the planet. It dissolves minerals, it carries nutrients, it creates environments where chemistry can become biology. But water alone is not enough. Earth's atmosphere contains oxygen in unusually high concentrations. This oxygen was not present in the early solar system. It was produced slowly over billions of years by photosynthetic life. Tiny organisms changed the composition of an entire planet. Oxygen made complex life possible, but it also introduced risk, fire, oxidation, instability. Earth remains habitable not because it avoids danger, but because it maintains balance. And balance is not guaranteed. Earth's size matters. If it were much smaller, gravity would be too weak to hold an atmosphere. If it were much larger, it might resemble a gas giant with crushing pressures. Earth is massive enough to retain air and water, yet small enough to remain geologically active. Structure matters as much as location. All of these processes unfold quietly beneath awareness. Most of the time, you are not thinking about axial tilt or magnetic fields or plate tectonics. You are thinking about ordinary things: work, family, sleep. And yet, these planetary systems continue operating without interruption. The fact that you can pause, reflect, and listen right now is not separate from Earth's design. It is a direct consequence of it. We often ask whether Earth is unique. Science has not answered that question yet. We have found thousands of planets orbiting other stars, but none that match Earth in all the same ways, not in the same combination, not over the same timescales. Earth is not perfect, it is dynamic, unstable in places, always changing. But for now, it holds a rare equilibrium, not because it was destined to, not because the universe favors life, but because a long chain of physical processes happen to align and continue aligning. In the vast silence of space, Earth does not demand attention. It simply offers conditions. And those conditions allow you to be here, listening, breathing, and thinking. In a universe shaped by chance and time, the quiet persistence of balance may be the rarest thing of all. When you move inward through the solar system toward the sun, you enter a region shaped by heat, gravity, and scarcity. These are the rocky worlds, built from metal and stone, orbiting close enough to the sun that every small difference in distance creates a dramatically different outcome. From far away, they may look similar. From within, each one tells a very different story about what a planet can become. Mercury is the closest. It moves through space in silence, locked in a slow rhythm that feels almost unnatural. One full rotation of Mercury takes longer than one full orbit around the Sun. A single day on Mercury lasts longer than its year. As a result, one side of the planet bakes under relentless sunlight while the other side sinks into deep, prolonged darkness. Temperatures swing between extremes that would feel impossible to endure. There is no thick atmosphere to soften the transition, no oceans to carry heat, no weather to redistribute energy. Mercury is exposed, direct, and uncompromising. It shows what happens when a planet exists too close with too little protection. Silence is also a kind of data. Venus, just slightly farther out, appears at first glance to be Earth's twin, similar in size, similar in composition, and yet its history diverges almost completely. Venus is wrapped in a dense atmosphere of carbon dioxide, thick enough to trap heat with extraordinary efficiency. This runaway greenhouse effect raises surface temperatures high enough to melt lead, even though Venus receives less sunlight than Mercury. The planet rotates slowly and in the opposite direction of most planets, with a day longer than its year. Clouds reflect sunlight back into space, but beneath them, the heat remains locked in. Whatever water Venus once had is long gone, lost to space as the planet overheated. Venus is a reminder that small differences can cascade over time, turning similarity into contrast. Space rarely gives us simple answers. Between these two extremes lies Earth, and its position is easy to underestimate. Earth is not calm because it is passive. It is calm because it is regulated. Its atmosphere is thick enough to retain heat, but not so thick that it traps it uncontrollably. Its rotation is fast enough to distribute energy, but not chaotic. Liquid water moves freely across its surface, carrying heat from equator to poles. Geological activity reshapes the surface and recycles material. Earth sits in a narrow balance, one that does not announce itself loudly but quietly sustains complexity. Numbers whisper more than they speak. From a human perspective, this balance becomes visible in ordinary moments, in predictable seasons, in breathable air, in a stable sky. You are not required to think about orbital mechanics to experience their outcome. You simply live within them. Earth does not demand attention through extremes. It allows attention to turn inward, outward, and toward meaning. Beyond Earth, Mars offers another variation. Smaller and colder, Mars once held rivers, lakes, and perhaps shallow seas. Today, it is marked by absence. Olympus Mons rises higher than any volcano on Earth, built over millions of years by slow eruptions that gravity could not suppress. Valles Marineris stretches across the surface like a scar, a canyon system so vast it dwarfs anything on Earth. These features speak of a time when Mars was more active, more dynamic. But Mars lost much of its atmosphere, likely due to a weakening magnetic field. As air thinned, water evaporated or froze. Climate stability faded. Mars became a world frozen in transition, preserving its past in plain sight. Together, these 4 planets form a sequence rather than a category. They show how outcomes change gradually with distance, size, and internal structure. Too close, and a planet is stripped and scorched. Too dense, and heat cannot escape. Too small, and protection fades. Earth is not the default. It is the exception within its own neighborhood. This is not a story of perfection. Earth has experienced ice ages, mass extinctions, and dramatic shifts. But compared to its neighbors, it has remained within boundaries that allow recovery. That resilience is subtle. It is built into systems that operate far below conscious awareness. And yet, those systems shape every human experience. As you listen, perhaps settling more deeply into rest, the inner solar system begins to feel less like a set of destinations and more like a lesson in variation. Each planet responds to the same star, the same laws of physics, and the same initial materials, yet arrives at a different result. No intention, no preference, only process unfolding over time. The rocky planets do not compete. They demonstrate. They show how structure, distance, and time interact quietly, shaping worlds without commentary. And among them, Earth remains a place where balance persists, not loudly, not permanently, but long enough for awareness to arise and wonder to take root. When most people imagine the asteroid belt, they picture a dense, chaotic region filled with tumbling rocks, a dangerous barrier between Mars and Jupiter where objects constantly collide. This image has been reinforced by science fiction for decades, but it does not match reality. The asteroid belt is not crowded. It is not violent. It is, for the most part, empty, vastly empty. If you were to travel through the asteroid belt in a spacecraft, you would not need to weave between obstacles. You would likely see nothing at all for long stretches of time. The average distance between large asteroids is hundreds of thousands of kilometers. Even the largest bodies are separated by space so wide that collisions are rare events, measured in millions of years. Silence is also a kind of data. The total mass of everything in the asteroid belt combined is surprisingly small. All of its material together amounts to less than the mass of Earth's moon. This includes the largest objects, such as Ceres, Vesta, and Pallas, as well as countless smaller fragments. If this material were gathered into a single body, it would not form a planet. There is simply not enough substance. For a long time, scientists believed the asteroid belt was the remains of a destroyed planet. The idea felt intuitive. A shattered world, broken apart by some ancient catastrophe. But as measurements improved, this explanation no longer held up. There was no missing mass, no energy signature, no evidence of a single planetary body that had ever existed there. Numbers whisper more than they speak. Instead, the asteroid belt represents something that never fully formed. In the early solar system, dust and rock were colliding and sticking together throughout the inner region. Planets were assembling through a slow process of accretion. But between Mars and Jupiter, that process was disrupted. Jupiter's gravity is immense. It outweighs all the other planets combined. During the early stages of planet formation, Jupiter's gravitational influence stirred the material in the asteroid belt region, increasing the relative speeds of collisions. When objects collide too fast, they tend to break apart rather than merge. Growth becomes fragmentation. Assembly becomes prevention. Space rarely gives us simple answers. Jupiter did not destroy a planet. It prevented one from ever becoming whole. Its presence kept the region dynamically unstable, ensuring that no single body could gather enough mass to dominate. The asteroid belt is not a graveyard. It is a record of interruption. From a human perspective, this can be difficult to grasp. We are used to thinking in terms of events, moments, and outcomes, but much of the solar system's structure is defined by what did not happen, by processes that were slowed, diverted, or quietly cancelled. The asteroids themselves preserve this history. Many are ancient, largely unchanged since the solar system's earliest days. They carry chemical signatures that predate the planets. In laboratories on Earth, fragments of asteroids are studied not because they are dramatic, but because they are honest. They are time capsules of formation. As you listen, perhaps becoming more still, the asteroid belt begins to feel less like an obstacle and more like a pause. A region where growth was held back, leaving behind a sparse collection of survivors orbiting in silence. This emptiness matters. It shaped the architecture of the solar system. It influenced the distribution of material. It helped define where planets could form and where they could not. In the vast design of space, absence is not a mistake. It is information. And sometimes, the most important structures are the ones defined not by what is there, but by what never came to be. As you move beyond the asteroid belt, the solar system changes character. The inner worlds are familiar in scale. Their surfaces can be imagined, their horizons pictured. But beyond this point, size stops behaving intuitively. The giant planets are not simply larger versions of the rocky worlds. They belong to a different category of reality, where mass reshapes space, gravity dominates architecture, and diversity emerges from scale itself. The first of these worlds is Jupiter. Jupiter is so massive that it holds more material than all the other planets combined. This is not a poetic exaggeration. If you were to gather every rocky world and gas giant except Jupiter and compress them together, they would still fall short of its mass. That single fact quietly redefines how the solar system works. Jupiter's gravity shapes the paths of asteroids, stabilizes or destabilizes orbits, and influences regions far beyond its immediate surroundings. Numbers whisper more than they speak. Jupiter has no solid surface in the way Earth does. Its visible layers are clouds, stacked and moving, driven by heat rising from deep within the planet. Among these clouds, the Great Red Spot has persisted for centuries. It is a storm larger than Earth, rotating steadily, not as an event but as a feature. On Jupiter, weather becomes geography. What would be temporary elsewhere becomes enduring here. space rarely gives us simple answers. Orbiting Jupiter is an entire system of worlds that feel almost like a miniature solar system of their own. Io is the most volcanically active body we know, its surface constantly reshaped by tidal forces that knead its interior like soft clay. Europa, by contrast, appears calm, its icy shell cracked into patterns that hint at a vast ocean beneath. And Ganymede is larger than the planet Mercury, with its own magnetic field, quietly asserting that moons can rival planets in complexity. Silence is also a kind of data. Together, these moons show how gravity creates variety. Jupiter does not merely dominate, it generates environments. Its presence stretches, heats, and shapes the bodies around it, turning simple ice and rock into active worlds. For humans studying from afar, this feels almost intimate. We see cause and effect written clearly across distance. Beyond Jupiter lies Saturn, a planet whose appearance often captures attention before its physics does. Saturn's rings are wide, bright, and structured, made of countless particles of ice and rock, each following its own orbit. They are thin on a cosmic scale, yet they define the planet's identity. The rings are not permanent. They are transient structures, likely to disperse over time. What feels eternal to us is temporary by planetary standards. Saturn's moons continue the theme of diversity. Titan has a thick atmosphere and lakes of liquid hydrocarbons on its surface. Chemistry unfolds there in slow motion, under orange skies, offering a glimpse of how complex molecules can form without liquid water. Enceladus, much smaller, ejects plumes of water vapor from cracks in its icy surface, revealing a warm ocean below. In these distant environments, habitability becomes a question of energy rather than sunlight. Numbers whisper more than they speak. Moving farther outward, the solar system grows colder and stranger. Uranus does not rotate upright like the others. Its axis is tilted by about 98 degrees, causing it to roll along its orbit rather than spin like a top. As a result, its seasons are extreme, with poles that face the sun for decades at a time, followed by long periods of darkness. The planet's pale blue color comes from methane in its atmosphere, absorbing red light and leaving behind a soft, distant hue. Uranus feels quiet in a way that is difficult to describe. Its heat output is low compared to other giant planets. Its atmosphere appears subdued. Yet its orientation makes it one of the most unusual bodies in the solar system. It reminds us that symmetry is not a requirement. Order does not imply uniformity. Space rarely gives us simple answers. At the edge of the giant planet region lies Neptune, a world defined by motion. Despite receiving very little sunlight, Neptune hosts the fastest winds in the solar system, with speeds exceeding 2,000 kilometers per hour. Energy circulates efficiently here, driven by internal heat rather than solar input. Neptune shows that distance from the Sun does not equate to inactivity. Silence is also a kind of data. Neptune's moon Triton adds another layer of complexity. Triton orbits in the opposite direction of Neptune's rotation, suggesting it was captured rather than formed in place. Its surface shows signs of cryovolcanism, where materials like nitrogen and water erupt instead of molten rock. Even at the solar system's edge, geology continues, reshaped by cold rather than heat. As a group, the giant planets expand the meaning of planetary diversity. They show how mass alters outcome, how gravity creates internal heat, how moons become worlds. Compared to the inner planets, these giants feel less personal, less relatable. And yet, their influence reaches inward, shaping the very conditions that allow smaller worlds to exist. For humans listening from Earth, The giant planets serve as a reminder that scale changes rules. What is rare nearby becomes common farther out. What feels stable becomes dynamic. The solar system is not built around our comfort or comprehension. It unfolds according to physical laws that do not prioritize familiarity. And as you rest with these thoughts, letting the rhythm slow, the giant planets stand not as destinations, but as markers of how vast and varied one system can be. In space, when scale increases, meaning does not disappear. It simply becomes quieter, deeper, and more patient. When you pass beyond Neptune, the solar system does not end. It softens. The clear structure of planets and orbits gives way to something more diffuse, more uncertain, a region where objects are spread thinly across enormous distances and time begins to feel stretched. Here, the solar system fades rather than stops, and that fading tells an important story. The first of these outer regions is the Kuiper Belt. It forms a broad, disc-like zone extending beyond Neptune's orbit, populated by icy bodies left over from the early days of planetary formation. These objects are not tightly packed. They move quietly, separated by vast distances, each following a slow, steady path around the Sun. Silence is also a kind of data. Among them is Pluto, once classified as the 9th planet, and later reassigned as our understanding deepened. Pluto's story is not one of loss, but of clarity. Its orbit is tilted and elongated, crossing paths with Neptune while remaining stable over long timescales. Pluto has mountains of ice, thin layers of atmosphere that appear and disappear with the seasons, and a surprisingly complex geology for a world so small and distant. Numbers whisper more than they speak. Another body in the Kuiper Belt, Eris, is similar in size to Pluto and even more distant. Its discovery forced astronomers to reconsider what it means to be a planet. The Kuiper Belt revealed that Pluto was not alone, but part of a broader population. The solar system had not been miscounted. It had been misunderstood. Space rarely gives us simple answers. The Kuiper Belt is important not because it is crowded, but because it preserves early material in a cold, relatively undisturbed state. These objects are remnants of the disk that once surrounded the young Sun. They are not debris from destruction, but survivors of formation, offering a record of how the outer solar system assembled and settled into its current shape. Beyond even this distant belt lies a region that is more conceptual than observed. The Oort cloud is thought to extend from roughly 2,000 astronomical units to as far as 100,000 astronomical units from the Sun. At that distance, the Sun is no longer a dominant presence. Nearby stars, galactic tides, and the slow movement of the Milky Way itself begin to matter. The Oort cloud is believed to be the source of long-period comets, objects that appear suddenly in the inner solar system, arriving from directions that seem almost random. These comets are nudged inward by distant gravitational influences, beginning journeys that take millions of years. When they finally pass near Earth, they carry with them material unchanged since the solar system's formation. From a human perspective, this is difficult to hold in mind. A region so vast that even light takes days to cross it. Objects so distant that they are barely bound to the Sun at all. And yet, this is still part of our system. Still connected, still responding, however weakly, to the Sun's gravity. Silence is also a kind of data. The Oort cloud represents the true gravitational boundary of the solar system, not defined by where planets stop, but by where the Sun's influence gradually gives way to the galaxy. There is no sharp edge, no line you can cross and say, "Now you have left." There is only a slow thinning, a gradual release. As you listen, perhaps feeling the pace of your thoughts slow, this outer region invites a different way of understanding. The solar system is not a compact arrangement of objects. It is a long gradient stretching outward into darkness, shaped as much by absence as by presence. We often imagine exploration as moving from place to place, from one solid surface to another. But beyond Neptune, exploration becomes something else. It becomes patience, it becomes inference, it becomes learning to read faint signals and subtle motions. At the far edges of the sun's reach, the solar system does not declare itself finished. It simply becomes quiet enough that you have to listen more closely to know it is still there. When we picture planets moving through space, we often imagine smooth circles, evenly spaced, turning like gears in a quiet machine. That image feels orderly and comforting, but it is not how motion actually works. In reality, planets follow elongated paths called ellipses, stretching closer to the Sun at one point and drifting farther away at another. This subtle asymmetry changes everything, even though it is almost invisible at first glance. The understanding of this motion comes largely from the work of Johannes Kepler, who realized that planetary orbits are not perfect circles. His laws describe how planets sweep out equal areas in equal times, meaning their speed is not constant. When a planet is closer to the Sun, it moves faster. When it is farther away, it slows down. This is not a choice or a correction. It is a natural response to gravity. Numbers whisper more than they speak. This changing speed is something you can feel if you imagine riding along with a planet. As it approaches the Sun, gravity pulls more strongly, drawing it forward and increasing its velocity. As it climbs away, that pull weakens and the planet eases into a slower pace. The motion is continuous and smooth, without sharp turns or sudden stops. Space rarely gives us simple answers. For humans, this has practical consequences. Spacecraft do not travel in straight lines toward their destinations. They follow carefully calculated arcs that borrow energy from gravity. Engineers plan trajectories that align with planetary motion, using speed changes that nature already provides. These paths are not shortcuts. They are negotiations with physics. One of the clearest examples of this is the launch window. A spacecraft cannot leave Earth for Mars at just any time. Earth and Mars must be positioned correctly, moving at compatible speeds along their orbits. When this alignment occurs, a window opens, sometimes for only a few weeks, allowing a spacecraft to transfer efficiently from one orbit to another. Miss the window and the wait begins again. Silence is also a kind of data. These windows reveal something important about the solar system. Motion is not random, but it is not static either. Everything is moving all the time, each object responding to gravity in its own way. The solar system is less like a map and more like a rhythm, with cycles that repeat over years, decades, and centuries. This rhythm shapes human experience in subtle ways. Missions are delayed, plans are adjusted, patience becomes part of exploration. Even with advanced technology, humans must wait for the right moment, respecting the timing written into orbital mechanics. Kepler's laws apply not only to planets, but to moons, asteroids, comets, and spacecraft. They describe a universal language of motion, one that does not change with scale. Whether an object is the size of a planet or a piece of metal launched from Earth, it follows the same rules. As you listen, perhaps feeling your own thoughts slow and settle, orbital motion begins to feel less abstract. It becomes a reminder that movement does not require urgency. Progress does not demand speed. Stability can emerge from constant change, as long as the pattern holds. The planets continue their paths tonight, accelerating and decelerating, tracing shapes that repeat without ever quite closing. They do not rush. They do not hesitate. They simply follow the geometry of gravity. And in that quiet consistency, the solar system teaches a gentle lesson. Motion does not need forceful intention. Sometimes, it only needs time, alignment, and the patience to wait for the moment when movement becomes effortless. When humans imagine traveling through space, it is easy to underestimate the role of time. Distance feels abstract, but duration feels personal. In space exploration, time is not a side effect. It is the primary constraint. Even within our own solar system, travel unfolds slowly, governed not by ambition, but by physics. A journey to Mars typically takes between 6 and 9 months. That range exists because Earth and Mars are always moving, sometimes closer, sometimes farther apart. A spacecraft must leave at the right moment, follow a curved path shaped by gravity, and arrive when Mars is there to meet it. During those months, the crew would live inside a confined environment, carrying everything they need, watching Earth shrink into a bright point behind them. Numbers whisper more than they speak, travel farther out, and time stretches dramatically. A mission to Jupiter takes roughly 5 to 6 years using conventional propulsion. The spacecraft does not accelerate continuously. It coasts, slowly exchanging energy with gravity, relying on carefully planned trajectories. During those years, technology ages, teams change, and priorities shift back on Earth. Space rarely gives us simple answers. Reaching Neptune requires even more patience. The fastest missions take around 12 years to arrive, and that is only to pass by, not to slow down and remain. By the time signals return to Earth, entire phases of human life have passed. Children become adults, scientists retire. The mission continues quietly, indifferent to these changes. Silence is also a kind of data. These long durations reveal something fundamental. Space travel is not about speed alone, it is about endurance. Spacecraft are built to survive isolation, radiation, and extreme temperatures for decades. They operate without maintenance, without rescue, without adjustment beyond what can be sent through delayed signals. Exploration at this scale is less like a sprint and more like a long vigil. It is tempting to assume that faster technology solves this problem, but speed itself has limits. The Apollo spacecraft, which carried humans to the Moon, reached speeds of about 11 kilometers per second relative to Earth. That was enough to escape Earth's gravity and return safely, but it would be insufficient for rapid travel across the solar system. The Parker Solar Probe, by contrast, achieves much higher speeds, exceeding 190 kilometers per second at its closest approach to the Sun. It becomes the fastest human-made object ever created. And yet, this speed does not translate into quick interplanetary travel. Parker moves fast only because it falls deeply into the Sun's gravity well. It is trading altitude for velocity, not racing outward across space. Numbers whisper more than they speak. This comparison reveals a subtle truth. High speed does not mean freedom of movement. Direction matters. Energy must be spent not just to go fast, but to go where you intend to arrive. Gravity assists, orbital transfers, and long coasting phases remain unavoidable. For humans, this has emotional consequences. Space travel demands acceptance of delay. Missions are planned decades in advance. Results arrive long after expectations are set. There is no immediate feedback, no instant reward. Understanding arrives slowly, sometimes too late for the people who began the journey. And yet, humans continue to launch spacecraft outward. Not because it is efficient, not because it is fast, but because curiosity outlasts convenience. As you listen, perhaps feeling the pace of your own thoughts ease, The scale of space travel invites reflection. Our technology allows us to reach astonishing distances, but only by aligning with the natural rhythms of the solar system. We do not overpower space. We cooperate with it. Every spacecraft traveling tonight is moving along a path written by gravity, time, and patience. It will arrive when it arrives. It will send its data when it can, and Earth will wait. In the quiet between launch and arrival, space exploration becomes less about conquest and more about commitment. A reminder that some journeys are measured not by speed, but by how long we are willing to keep listening. Long before there were planets, or orbits, or names, the solar system began as a quiet cloud. A cold, diffuse region of gas and dust drifting within the Milky Way, barely distinguishable from its surroundings. This cloud, often called the solar nebula, did not announce itself as a beginning. It simply existed, waiting for conditions to change. At some point, a disturbance passed through. Perhaps a nearby stellar explosion, perhaps the slow compression of interstellar material. Gravity began to matter more than motion. The cloud collapsed inward, not suddenly, but gradually, spinning faster as it shrank. At the center, pressure and temperature increased, forming the early sun. Around it, a flattened disk of material spread outward, thin and wide, carrying the raw ingredients of everything that would follow. Silence is also a kind of data. Within this disk, tiny grains of dust began to collide and stick together. Electrostatic forces helped at first, allowing particles smaller than sand to form clumps. Over time, these clumps grew into pebbles, then rocks, then kilometer-scale bodies known as planetesimals. This process is called accretion, but the word hides its patience. Growth happened through countless small interactions, each one insignificant on its own, yet decisive in accumulation. Numbers whisper more than they speak. Closer to the sun, heat limited what could survive. Only metals and rocky compounds remained solid. Farther out, beyond a certain distance known as the frost line or ice line, temperatures dropped low enough for water, ammonia, and methane to freeze. Ice added mass quickly. Objects beyond this line grew faster and larger, giving rise to the giant planets. Location determined opportunity. This separation explains much of the solar system's structure: small rocky worlds inside, massive gas and ice giants outside. But this is only part of the story. For a long time, scientists assumed the planets formed roughly where we see them today. That idea felt neat and intuitive. But evidence began to suggest something more dynamic. Orbits did not always stay where they began. Space rarely gives us simple answers. As the giant planets formed, they interacted strongly with the surrounding disk of gas and debris. These interactions caused them to migrate, slowly shifting their orbits inward or outward over millions of years. Jupiter may have moved closer to the Sun before drifting back outward. Saturn's motion likely played a role in stabilizing this process. These migrations reshaped the distribution of material, scattering some objects inward and flinging others far into the outer regions. This movement helps explain why the asteroid belt is sparse, why Mars is smaller than expected, and why distant reservoirs of icy bodies exist. The solar system we see today is not a frozen snapshot of formation, it is the result of rearrangement. From a human perspective, this idea can feel unsettling. We tend to imagine beginnings as orderly and outcomes as fixed. But planetary systems are shaped by adjustment, feedback, and long periods of instability. Stability emerges late, not early. During this time of migration, the inner solar system experienced what is known as the Late Heavy Bombardment. asteroids and comets were redirected toward the rocky planets, colliding with their surfaces over hundreds of millions of years. These impacts reshaped crusts, created basins, and delivered volatile materials. Water, and perhaps organic compounds, arrived not gently but persistently. Silence is also a kind of data. On Earth, evidence of this era has mostly been erased by erosion and plate tectonics. On the Moon, it remains visible in craters that have not changed for billions of years. These scars are records not of destruction alone, but of delivery. Without this bombardment, Earth might be drier, less chemically rich, less capable of sustaining complexity. Formation and migration are not separate phases. They overlap, influence one another, and continue longer than intuition suggests. Even after the gas disk dissipated, gravitational interactions persisted. Orbits shifted. Resonances formed. Some bodies were ejected entirely, becoming interstellar wanderers. From the quiet of your listening space, this may feel distant, but it is not disconnected. The ground beneath you, the water around you, the chemistry inside your body all trace back to these early motions, to dust that stuck, to ice that survived, to planets that moved when movement mattered most. The solar system did not form as a finished design. It assembled itself while in motion, correcting, redistributing, and settling over time. What appears stable now is the result of long negotiation between gravity and chance. As your thoughts slow, consider this gently. The place you inhabit was not inevitable. It was shaped by processes that allowed variation, disruption, and recovery. The solar system learned its structure by moving through uncertainty, and perhaps that is its quiet lesson. Order does not require stillness. Sometimes it emerges only after a long period of change, when motion finally gives way to balance, and balance becomes something that can last. Impacts are often imagined as sudden interruptions, moments when space intrudes violently into planetary calm. But in the history of the solar system, impacts are not exceptions. They are part of the ongoing exchange between worlds and the material that surrounds them. Over billions of years, planets have been shaped not only by internal processes, but by what arrives from beyond. One of the most well-known examples is the impact that created the Chicxulub crater. Around 66 million years ago, a large asteroid struck what is now the Yucatan Peninsula. The event coincided with a major mass extinction, including the disappearance of non-avian dinosaurs. The crater itself was hidden for a long time, buried beneath layers of sediment, discovered only through careful measurement and patient investigation. Silence is also a kind of data. This impact is often remembered for what it ended, but that is only part of the story. Long before Chicxulub, countless smaller impacts shaped Earth's surface and chemistry. During the early solar system, asteroids and comets delivered water and organic compounds to the rocky planets. These materials did not arrive all at once. They arrived gradually, over immense spans of time, accumulating into oceans and complex chemistry. Numbers whisper more than they speak. Comets, in particular, carry ices that formed far from the sun. When they travel inward, they bring with them frozen water, carbon compounds, and other volatiles. Each passage leaves behind a trace, a small contribution to planetary inventories. Earth's oceans are likely the result of both internal processes and external delivery, a blend rather than a single source. Meteorites that fall to Earth today are fragments of this ancient history. Some are pieces of asteroids that never became planets. Others come from differentiated bodies, even from Mars or the Moon, launched into space by earlier impacts. When scientists study these rocks, they are not looking for spectacle. They are reading records. Each sample preserves conditions from a time before Earth had continents, before life reshaped the atmosphere. Space rarely gives us simple answers. In the present day, impacts continue, though at a much slower pace. Most objects that enter Earth's atmosphere burn up harmlessly. Larger ones are rare, but they are not ignored. Astronomers track near-Earth objects, known as NEOs, cataloguing their orbits and monitoring potential future encounters. This work is quiet, methodical, and ongoing. It is not driven by fear, but by awareness. The act of tracking these objects changes how humans relate to space. We are no longer passive observers of the sky. We are participants in a system where prediction and preparation matter. Understanding motion becomes a form of protection. This shift is reflected in missions designed not to explore, but to test response. The Double Asteroid Redirection Test, often called DART, was a deliberate experiment in planetary defense. A spacecraft was sent to collide with a small asteroid moon, not to destroy it, but to slightly alter its orbit. The change was measured, subtle, and successful. For the first time, humans demonstrated the ability to influence the trajectory of a natural object in space. Silence is also a kind of data. What matters about this experiment is not power but precision. The goal was not control but understanding. How much force is required, how momentum transfers, how materials respond. These are questions answered slowly through observation rather than assertion. Impacts remind us that Earth exists within a dynamic environment. Space is not a distant backdrop. It is an active participant in planetary history. The same processes that delivered water and organic compounds also brought disruption. The same mechanisms that threaten also enable. From a human perspective, this balance is difficult to accept. We prefer clear categories of good and bad, benefit and danger. But nature does not organize itself that way. The solar system operates through exchange, through collisions that create and collisions that erase. As you listen, perhaps feeling the weight of time soften your thoughts, consider this gently. Life on Earth is connected to objects that once traveled through cold, distant regions of space. The ground beneath you carries traces of those journeys. Your presence is linked to events that unfolded long before memory or record. In the quiet rhythm of cosmic motion, impacts are not interruptions. They are conversations, slow and ongoing, between worlds that share the same space, shaping one another across time. For most of human history, the planets we knew were limited to a single system. The night sky suggested stars were distant lights, separate and unreachable, each one alone. That assumption began to change only recently. In the past few decades, astronomers have confirmed the existence of thousands of planets orbiting other stars. These are exoplanets, worlds beyond our solar system, each one moving quietly around its own sun, following the same laws of gravity that shape our own neighborhood. The discovery of exoplanets did not arrive all at once. It came through careful measurement, tiny shifts in starlight, subtle dips in brightness, and small changes in motion that revealed the presence of unseen companions. Many of these planets are unlike anything we see nearby. Some orbit extremely close to their stars, completing a year in days. Others are massive gas giants drifting far from their suns. There are planets hotter than molten rock and others colder than deep space itself. Numbers whisper more than they speak. Among this growing catalogue, one question quietly persists. Is there another Earth? So far, the answer remains uncertain. Astronomers have found planets similar in size to Earth, planets within regions where liquid water could exist, and planets with rocky compositions. But similarity in one property does not guarantee similarity in outcome. A planet can be the right size and still lack an atmosphere. It can orbit at the right distance and still be sterile. Space rarely gives us simple answers. The challenge is not only finding planets, but understanding them. Distance limits detail. Most exoplanets appear as single data points, not images. We know they exist because of their effects, not their appearance. And yet science continues to move forward, gradually extending perception into regions once thought unreachable. A major step in this effort comes from the James Webb Space Telescope, which allows scientists to study the atmospheres of distant planets by analyzing starlight as it passes through them. This light carries chemical signatures, faint fingerprints of molecules such as water vapor, carbon dioxide, methane, and oxygen. By measuring these patterns, researchers can infer conditions on worlds light years away. Silence is also a kind of data. These measurements are not declarations of life, they are hints. A planet with water vapor is not automatically inhabited. A trace of methane does not confirm biology. Many processes can produce similar signals. The task is to distinguish between chemistry shaped by geology and chemistry shaped by life, a distinction that requires patience and restraint. From a human perspective, this caution matters. We are inclined to hope for quick confirmation, for a clear answer that resolves uncertainty. But the universe rarely offers that kind of clarity. Instead, it provides layers of probability, requiring interpretation rather than certainty. The search for life beyond Earth is not a race to discovery. It is a gradual refinement of questions. What conditions allow complexity? How long stability must persist? How energy flows through planetary systems? These questions do not point to a single target. They describe a process. In this sense, Earth remains our only complete example. It shows that life can arise when chemistry, time, and environment align. It does not prove that this outcome is common. It only demonstrates that it is possible. As scientists study exoplanet atmospheres, they also learn more about Earth itself. Comparing distant worlds sharpens our understanding of what makes our planet function as it does. Differences become informative. Absences become meaningful. Numbers whisper more than they speak. From where you are listening, perhaps settling deeper into quiet, it can be comforting to know that the search for life elsewhere does not diminish Earth's value. It enhances it. Each new discovery adds context rather than replacement. Each distant planet expands perspective rather than competition. The night sky is no longer a collection of unknown lights. It is a map of potential systems, most of them uninhabited, some of them incomplete, and a few that invite closer attention. None of them have yet revealed a second Earth, and that absence carries its own message. In a universe filled with planets, life may require more than the right ingredients. It may require time, balance, and persistence on scales we are only beginning to understand. As this chapter closes, the search continues quietly, guided by data, shaped by restraint, and grounded in curiosity rather than expectation. The question of life beyond Earth remains open, not as a mystery demanding resolution, but as an invitation to keep listening, patiently, to what the universe is willing to reveal. The solar system feels stable because human time is short. Orbits repeat, seasons return. The sun rises and sets with reassuring regularity. But stability in space is always temporary. Even the most familiar systems are moving toward outcomes shaped by physics rather than permanence. At the center of this future is the sun. The sun is about halfway through its life. It has been shining for roughly 4.5 billion years, converting hydrogen into helium in its core, releasing energy steadily and predictably. This process will continue for billions of years more, but it will not last forever. When the hydrogen fuel in the core becomes depleted, the balance between gravity and pressure will change. Space rarely gives us simple answers. As fusion slows in the core, gravity will compress it, raising temperatures and igniting hydrogen in surrounding layers. The sun will expand outward, becoming a red giant. Its outer atmosphere will swell, reaching far beyond its current size. Mercury and Venus will be lost. Earth's fate is less certain, but survival does not imply habitability. Even if Earth avoids direct engulfment, conditions will change long before that moment. As the sun brightens, Earth's oceans will evaporate. Water vapor will break apart under ultraviolet radiation. Hydrogen will escape into space. The planet will lose its ability to regulate temperature. Life as we know it will no longer be possible. Numbers whisper more than they speak. This transformation will not be sudden. It will unfold over hundreds of millions of years, slowly enough that no single generation could witness it. From a human perspective, it is unimaginably distant. From a cosmic perspective, it is routine. As the red giant phase ends, the sun will shed its outer layers, releasing them gently into space. These layers will form a glowing planetary nebula, expanding outward, illuminated by the remaining hot core. Despite the name, planetary nebulae have nothing to do with planets. The term comes from early telescopes and human habit. Silence is also a kind of data. At the center of this nebula, the sun's core will remain as a white dwarf, dense, hot, slowly cooling. It will no longer produce energy through fusion. It will simply persist, radiating stored heat into the surrounding darkness for trillions of years. By that time, the solar system will be a very different place. Orbits will have shifted slightly as the sun loses mass. The outer planets will drift outward. The inner system will be stripped and altered. Earth, if it still exists, will be a dry, airless remnant, carrying little resemblance to the world you know. This future is not a failure, it is a continuation. Stars are not designed to sustain life indefinitely. They are engines that operate for a time, creating conditions that allow complexity to arise, and then they change. The same processes that made life possible also guarantee that those conditions will eventually fade. From a human perspective, this can feel unsettling. We are drawn to the idea of continuity, of permanence. But the universe does not promise either. It offers opportunity within limits. And yet, there is something quietly grounding in this knowledge. Earth's habitability is not infinite, which gives the present moment meaning rather than fragility. The fact that conditions exist at all, for as long as they do, is not trivial. As you listen, perhaps letting your thoughts slow and soften, consider this gently. The future of the solar system is written not in endings, but in transitions. The sun will change. The planets will respond. Matter will rearrange itself into new forms. Long after life on Earth has ended, the remnants of this system will still move through the galaxy, carrying atoms forged in stars, shaped by time, and briefly organized into something that could wonder about its own place. In space, nothing is held forever. But for a while, balance exists, and sometimes that is enough. When you think about where you are, it is natural to begin with familiar scales: a room, a building, a city, a planet. But in astronomy, location expands outward in layers, each one revealing that what felt central is simply part of something larger, quieter, and far less concerned with boundaries. Earth orbits the sun, and the sun is one of hundreds of billions of stars within the Milky Way. From the inside, the Milky Way appears as a faint band of light across the night sky. a soft reminder that our star is embedded in a vast rotating disk of stars, gas, and dust. The Sun does not sit at the center. It moves along a wide orbit in the galaxy's outer regions, completing one full rotation roughly every 230 million years. Numbers whisper more than they speak. The Milky Way itself is not alone. It belongs to a small collection of galaxies known as the Local Group. This group includes a few dozen galaxies, among them the Andromeda Galaxy and many smaller companions. They move together through space, bound by gravity, slowly interacting over billions of years. The Local Group is not crowded. Distances between its members are immense, and interactions unfold on timescales that dwarf human history. Silence is also a kind of data. On even larger scales, the Local Group is part of a vast structure called Laniakea Supercluster. Laniakea is not a cluster in the traditional sense, but a region defined by gravitational flow, where galaxies move toward common centers of mass. It stretches across hundreds of millions of light-years and contains tens of thousands of galaxies. From this perspective, the Milky Way is no longer a dominant feature, but a single current within a much larger cosmic pattern. Space rarely gives us simple answers. As scale increases, structure becomes less solid and more statistical. Galaxies trace filaments, voids open between them. Matter gathers in ways that are visible only when averaged across enormous distances. These patterns are not designed. They emerge from gravity acting over time, shaping the distribution of matter after the universe's earliest moments. Beyond even these structures lies the observable universe. This is not the entire universe, but the portion from which light has had time to reach us since the beginning of cosmic expansion. Its boundary is defined not by a physical edge, but by time itself. The farther you look, the farther back you see, until light can no longer bridge the gap. From a human perspective, this idea can feel abstract, but it has a simple consequence. There are regions of the universe that exist beyond our ability to observe, not because they are hidden, but because the universe has not allowed enough time for information to travel. Knowledge, like light, has a horizon. Numbers whisper more than they speak. When you place yourself within this hierarchy, something subtle happens. Earth becomes smaller but not insignificant. The solar system becomes one arrangement among many. The Milky Way becomes one galaxy among billions, and yet this does not erase meaning. It reframes it. You are not at the center of the universe, but you are at a location where the universe can be observed, studied, and reflected upon. Awareness arises not from position, but from condition. The fact that you can trace these layers at all is part of the story. As you listen, perhaps feeling the weight of scale settle gently rather than heavily, consider this. Location in the universe is not about prominence, it is about perspective. From where you are, the universe is visible, measurable, and open to quiet understanding. In a cosmos too large to hold in thought all at once, knowing where you stand is less about orientation and more about humility. A calm recognition that being somewhere, rather than nowhere, is already a remarkable place to begin. When we talk about the universe, we often speak in terms of distance, light years, galaxies, vast scales that stretch the imagination outward. But time is the deeper dimension. Time is what gives those distances meaning. Without time, the universe would be static, silent, unfinished. The universe is about 13.8 billion years old. That number is not an estimate pulled from intuition. It comes from careful measurements of cosmic expansion, background radiation, and the distribution of galaxies. It represents the amount of time that has passed since the universe became transparent to light, allowing information to travel freely. Before that moment, The universe existed, but it could not yet be seen. Numbers whisper more than they speak. 13.8 billion years is not just a long duration. It is a framework. Within it, stars formed, lived, and died. Galaxies assembled. Elements heavier than hydrogen were forged in stellar cores and scattered into space. Planets condensed from dust. Chemistry became complex enough to support life. Each step required time, and not a little of it. Against this backdrop, human history occupies an almost vanishingly small interval. If you compress the age of the universe into a single calendar year, modern humans appear in the final minutes of the last day. Written language arrives seconds before midnight. Recorded history barely registers. Silence is also a kind of data. This does not diminish human experience, it contextualizes it. We often think of ourselves as late arrivals, and in a sense, that is true. But we are not early or late in any intentional way. We exist at a moment when the universe is mature enough to support complex structures, stable stars, and long-lived planetary systems. Too early, and there would be no heavy elements. Too late, and the universe would grow too diffuse, too cold, too quiet. Space rarely gives us simple answers. From a scientific perspective, this timing is sometimes called a coincidence, but coincidence does not imply meaninglessness. It simply reflects the interplay between physical processes unfolding at different rates. The universe does not rush. It takes the time it needs. Human time, by contrast, feels fast. Lives unfold quickly. Generations pass. Memory fades. We measure our existence in years and decades, while the universe measures in billions of years. This mismatch can feel disorienting, but it also invites a kind of calm. You do not need to match the universe's pace to belong within it. As you listen, perhaps settling deeper into rest, consider how much has already happened without awareness. For most of cosmic history, there were no observers. Stars formed and died in silence. Galaxies collided without record. The universe expanded without reflection. Awareness, when it arises, is rare. Not rare because life is necessarily unique, but because it requires stability over long periods, chemistry that persists, and conditions that allow information to be processed and remembered. These requirements are not trivial. They take time to align. Numbers whisper more than they speak. From this perspective, human existence is not fragile because it is brief. It is remarkable because it occurs at all. The universe does not owe awareness a place. It does not guarantee memory. And yet, for a short interval, it allows both. This rarity does not demand urgency or anxiety. It invites attentiveness. If moments are limited, they gain texture rather than pressure. Presence becomes more meaningful than permanence. Cosmic time does not judge. It does not hurry. It does not wait. It simply continues, carrying stars, planets, and occasional moments of reflection along with it. As this chapter closes, let this thought rest gently. In a universe that has existed for nearly 14 billion years, you are here for a brief span, at a moment when the universe can be known, studied, and quietly contemplated. And sometimes, rarity is not a burden to carry, but a quiet reason to listen more closely while the moment lasts. The universe is not designed to be gentle, but neither is it hostile. It operates through physical processes that unfold without intention, without awareness of consequence. From a human perspective, some of these processes appear as risks, events that could alter life on Earth if conditions align in a particular way. Understanding them does not create fear, it creates context. One of the most familiar cosmic risks is impact. Asteroids and comets continue to move through the solar system, following predictable orbits shaped by gravity. Most are small. most never come close to Earth. On rare occasions, larger objects cross paths with our planet. These events are spaced far apart in time, separated by millions of years. When they occur, they are not sudden intrusions, but the natural outcome of long-established motion. Silence is also a kind of data. Another influence arrives not from solid bodies, but from the sun itself. Solar storms driven by changes in the sun's magnetic field release streams of charged particles into space. When these particles reach Earth, they interact with the planet's magnetic field and atmosphere. Most of the time, the result is subtle, perhaps visible as auroras near the poles. Occasionally, stronger storms can disrupt satellites, radio communication, and power systems. These effects remind us that Earth is not isolated from its star. It is connected, continuously and quietly. Space rarely gives us simple answers. Far more distant and far less likely are gamma-ray bursts. These are among the most energetic events known, produced by collapsing massive stars or merging neutron stars in distant galaxies. Their energy travels across vast regions of space in narrow beams. The likelihood of one being aimed directly at Earth is extremely low. The universe is large and such alignments are rare, but their existence illustrates scale. Forces operate in the cosmos that dwarf anything humans can generate, yet they unfold so far away that they remain background rather than threat. Numbers whisper more than they speak. Another possibility exists in the form of rogue planets, worlds that drift through space without orbiting a star. These objects are thought to be common in the galaxy, ejected from their original systems during early gravitational interactions. A rogue planet passing through the solar system could, in theory, disturb orbits if it came close enough, but space is vast. Distances between stars and planets are immense. Encounters are statistically unlikely, separated by timescales far beyond human history. From a human point of view, these risks can sound abstract. They do not arrive with schedules, they do not announce themselves in advance, and yet science does not treat them as unknowns. Astronomers monitor near-Earth objects. Solar activity is observed continuously. High-energy events are catalogued across the universe. Understanding replaces speculation. Silence is also a kind of data. What is striking is not how dangerous the universe is, but how stable Earth's environment has been for so long. Conditions that allow complex life have persisted through eras marked by change, variation, and occasional disruption. Stability emerges not from the absence of risk, but from the rarity of alignment. As you listen, perhaps feeling the pace of thought slow, these cosmic risks begin to feel less like threats and more like reminders. Earth exists within a dynamic system. It is not sheltered by design, but by probability and distance. The same universe that allows stars to form also allows long intervals of calm. Understanding these risks does not diminish peace, it deepens it. Awareness replaces uncertainty. Perspective replaces urgency. In the quiet rhythm of cosmic time, danger is not constant, it is occasional. And the space between events is where life unfolds. Sometimes, knowing that the universe carries both power and patience is enough to let the mind rest, grounded in the understanding that calm is not the absence of motion, but the presence of balance, sustained quietly for now. For most of the universe's history, there were no witnesses. Stars formed and faded without being named. Planets circled quietly without maps. Space unfolded without record. And then, for a brief moment in cosmic time, a species emerged that felt compelled to look outward and leave something behind. Human exploration of space is often described in terms of technology and achievement, but beneath those details lies something simpler: curiosity. a quiet insistence on understanding what exists beyond immediate experience. This curiosity does not rush. It accumulates slowly, shaped by questions rather than answers. One of the clearest expressions of this impulse travels far beyond the planets carried by the Voyager spacecraft. Attached to each is a golden record, a physical message placed deliberately for no known recipient. It contains sounds of Earth, images of life, music from different cultures, and greetings spoken in many languages. It is not a broadcast, it is a gesture. Silence is also a kind of data. The golden record does not explain humanity in full. It cannot. It offers fragments, a heartbeat, a laugh, a greeting. It assumes that meaning, if it is ever found, will be assembled patiently by whoever listens, or perhaps by no one at all. Space rarely gives us simple answers. Alongside this message is another, quieter acknowledgement. A small plaque honoring the people who built and launched these missions, names etched into metal, carried outward as the spacecraft move farther from Earth each year. These names are not declarations of conquest. They are reminders that exploration is a collective effort built from countless ordinary contributions layered over time. Numbers whisper more than they speak. From a human perspective, Voyager's journey feels immense. Decades of travel, billions of kilometers crossed, signals that take hours to reach Earth, and yet, measured against cosmic time, Voyager's motion is gentle. It drifts rather than charges. It listens more than it announces. What matters is not how far it goes, but that it continues at all. The message Voyager carries is not about dominance or permanence. It does not claim ownership of space. It does not ask for response. It simply says that at one moment in time, on a small planet orbiting an average star, there were beings who wondered if they were alone, and who chose to send a quiet introduction into the dark. This choice reflects something enduring about humanity. Even knowing that answers may never come, we still reach outward. Even understanding that our messages may outlast us, we still compose them. Exploration, at its core, is not about arrival. It is about expression. As you listen, perhaps settling deeper into stillness, consider how modest this gesture truly is. A small object, moving slowly, carrying a record that could remain unread forever. And yet, it matters. Not because of what it will achieve, but because of what it represents. It represents a moment when awareness looked beyond itself and chose to acknowledge the universe rather than ignore it. Humanity's message to space is not loud. It is careful. It is incomplete. It is open-ended. It says, in effect, this is who we were when we decided to listen, and this is what we thought might be worth remembering. In the vast quiet of interstellar space, Voyager continues its path, carrying with it not certainty, but intention. And perhaps that is the most human thing we have ever sent into the universe. Not proof that we are important, but evidence that we were curious enough to ask and patient enough to wait without needing an answer in return. For much of human history, understanding the universe meant placing ourselves at its center. The Earth felt solid and unmoving. The sky appeared to turn around us each night, carrying the sun, the moon, and the stars in predictable arcs. This view, known as the geocentric model, was not born from arrogance, it was born from experience. When you stand on the ground, stillness feels natural. Over time, careful observation began to introduce tension into that certainty. Planetary motions did not behave as expected. Small irregularities accumulated. Patterns resisted simple explanation. Eventually, a different idea emerged. Earth was not the center. It was one of several planets orbiting the Sun. This heliocentric model did not immediately feel intuitive, but it explained what observations quietly revealed. Space rarely gives us simple answers. Accepting this shift required more than new equations. It required a change in perspective. The sky was no longer a stage built around humanity. It became a system governed by motion and gravity, where Earth moved along with everything else. This realization didn't make the universe colder, it made it more coherent. As telescopes improved, another layer unfolded. The stars were no longer distant points fixed to a single sphere. They became suns in their own right, scattered across immense distances. The Milky Way transformed from a hazy band into a vast galaxy filled with hundreds of billions of stars, and even that galaxy turned out not to be unique, but one among countless others. Numbers whisper more than they speak. With each expansion of scale, humanity's position shifted again. From center to participant, from participant to observer within a much larger structure. These changes were not driven by philosophy alone. They were driven by data, collected patiently, often resisted at first, then slowly accepted. The final and perhaps most profound shift came with the realization that the universe itself has a history. It is not eternal in a static sense. It is expanding. Galaxies are moving away from one another. Background radiation fills space with a faint echo of an earlier, denser state. These observations led to the Big Bang model, which describes the universe as evolving from a hot, compact beginning into the vast structure we observe today. Silence is also a kind of data. This idea does not describe an explosion in space, but an expansion of space itself. It places time alongside distance as a fundamental dimension of understanding. The universe is not just large, it is old, and it has changed. What is striking about this progression is not how wrong earlier models were, but how reasonable they were given the information available at the time. Scientific understanding does not leap. It inches forward, revising itself when evidence requires it. Each model is a step, not a failure. From a human perspective, this history carries a quiet lesson. Knowledge grows by letting go of certainty. Progress comes not from defending position, but from adjusting it. As you listen, perhaps feeling the calm of accumulated insight, consider how far awareness has traveled. From a stationary Earth beneath a turning sky, to a planet in motion, to a galaxy among many, to a universe with a beginning and a direction. Understanding did not arrive all at once. It arrived slowly, carried by observation, patience, and the willingness to listen when the universe answered softly rather than clearly. And perhaps that is the enduring pattern. Each time we learn something new about the cosmos, we find ourselves smaller in position, but richer in perspective, reminded that clarity does not come from standing at the center, but from learning how to see without needing to be. As this journey through the solar system settles, one impression remains clearer than all the details. Space is vast and most of it is empty. The planets, the moons, the dust and the light are scattered across distances so large that emptiness becomes the dominant feature. What we call a system is in reality a wide field of silence, held together by gravity and time. Numbers whisper more than they speak. Within that emptiness, Earth is easy to overlook. It is small. It does not dominate its surroundings. It does not announce its presence beyond a thin layer of atmosphere and a faint magnetic field. And yet, among all the space we have observed, Earth remains unusual, not because it is dramatic, but because it maintains balance. Liquid water persists, chemistry remains active. Stability lasts long enough for awareness to emerge. Space rarely gives us simple answers, but here, conditions align quietly. Understanding scale changes how value is perceived. When distance stretches beyond intuition, closeness gains meaning. When time extends beyond memory, moments gain texture. Earth's rarity is not about perfection, it is about duration. About how long delicate systems can continue without collapsing, long enough for thought, curiosity, and reflection to appear. Silence is also a kind of data. From a human perspective, recognizing the size of the solar system and the vastness beyond it does not diminish life. It sharpens it. Awareness grows when context expands. Knowing how much space exists around us makes the presence of life feel less ordinary, not more fragile, but more precise. A condition met within narrow limits, sustained quietly for now. As you rest with these thoughts, allow them to remain open rather than resolved. The universe does not ask to be concluded. It continues, indifferent and patient. But within it, there is a small place where understanding is possible, where questions can be asked softly, and where meaning does not need to be permanent to be real. In a cosmos shaped mostly by emptiness, life gains value not by scale, but by presence. A reminder that understanding how large the universe is can quietly teach us how precious it is to be here at all.